All right, so I think I can start right now. I think my last name starts with a Z, so I'm always the last person to talk, apparently. So today's talk is on the hybrid learning in games with application to network security. So the outline of this talk is I can talk well. I have been talking about this topic in the CDC, so I start with the motivation and why. I'll just talk about why the network security problem is actually the one that inspires us to do this work. And then we talk about some of the ideas that we can convey in this talk. And also, the thing I would really want to highlight is that we're going to really look at the two things. One is the Papadimitrios puzzle, and the other one is the mean field learning. Hopefully, these are the 2 points that keep you awake. So let me just tell you the story why this is an interesting thing for us to investigate. So we start off looking at the game theory and want to see whether it is how to make it practical for the applications. So in game theory, usually people have to assume that you have the knowledge of the payoff function and you have to know the action space of others. For example, if you look at the battery response dynamics, you usually assume that you have to know what's the payoff function of other people. But usually it's not really true that you can actually know the payoff function of your own payoff, and also you possibly don't even know what is the payoff function of the other people. At the same time, you possibly do not even know what is the action space of other people. But in the fictitious play algorithm, for example, you actually have to know what is the action that has been played by other people. So also, at the same time, players do not really play the game at all the time. Some people might not really choose to do anything at a certain time instant. So interactions between the players can occur at random times. And also, players might have different learning capabilities and also different learning styles. So one of the problems that motivates us to look at this problem is the security problem. When you think about in the security problem, there's one attacker, and there's also an administrator. And thinking about a case where you do not even know what the attacker is doing, and you still want to play the game. So eventually, you do not know what is the game you're playing, or you do not know what is the action space of the strategy space of the attacker, and also you do not even know what is your utility function, because there's no predefined utility function saying that it's x squared or x cubed, but you have to learn on the way. So the framework that we're looking at is the zero-sum stochastic games with incomplete information. The incomplete information comes from, well, you do not know the network environment. It might be time varying. And also the stochastic games, because the state might be changing all the time. And also you do not know what the attacker is doing. The problem actually is very, if you look at the application, it can be applied to so many arenas in the security policy making. For example, the IDS configurations, honeynet deployment, and the routing protocols and the privacy setting on Facebook, for example. So the players also think about the administrators and attackers. They might have a different rationality intelligence. The attacker might be more intelligent sometimes, while sometimes they could be very dumb. And you do not know what is the intelligence of the attacker. And you might know what's your intelligence of yourself, but you might not know the intelligence of the attacker. And also, the learning rates is also important. So you might learn a lot faster if you have a lot of resources that has been invested into the infrastructure. The attacker might be learned slower if he's only attacking on his own. Well, it really depends on what are the resources and what are the capabilities of learning. So these attackers and administrators might learn at a very different rates. So this is the framework that we're looking. We are looking at a two-person zero-sum stochastic game model. Now, actually, the model doesn't need to be zero-sum. They can actually, the goals might not be aligned. So the game is composed of 4 components. One is the state, so the state space, where you assume that it is finite. And A1 and A2, there are action spaces, or P1 and P2. And P1 is the maximizer. Basically, for example, it is the administrator which maximizes its well-being of the system. And P2 is a minimizer, which try to bring or compromise an entire system down. So we're looking at the mixed strategies F and G. F is for P1, is a mixed strategy for P1, which is the distribution on the finite action space. Here we assume the action space is finite, and also G is the distribution on the finite action space of A2. Well, having this game in mind, we know there exists a equilibrium or a settle point equilibrium. So the settle point equilibrium is basically if you deviate from, for example, if F star and G star is the equilibrium, And if you try to deviate from that strategy, you're going to get worse payoff. So this is what the saddle point equilibrium is. If you try to imagine it using a potato chip, this is actually the point where it's actually in the middle of the potato chip. Okay, so this is the learning algorithm that we're looking at. So each agent or each player start with the initializing F0 and G0. So they start at a certain value. And then according to the initial condition or the previous mixed strategies, they're trying to generate an action. For example, I'm going to choose A1T with some probability using this distribution, and the other person is also going to choose an action using that particular distribution. And they both observe the instantaneous payoff. So for the person 1, he is going to observe this payoff. For person 2, he is going to observe the negative of that payoffs, because I'm looking at a zero-sum game. But the framework doesn't need to be a zero-sum, but in a zero-sum framework, it's easier to analyze the saddle point equilibrium. So after that, they're going to update the FT and GT according to what they observe. Just keep in mind that, well, at this moment, they do not need to know what is their utility function, because what you do is just observe what you get. You do not know what's your utility function, you just see what you get. And also, you do not know what the other people are playing, because you only observe the instantaneous payoff, because you do not know what is the action has been played by other people. You might infer, but you do not know what is really the action has been taken by other people. And the second thing you do is try to estimate the average payoff. And then you just go around this loop over and over again, so until it reaches some equilibrium. Well, here this is learning scheme, we call it a Gotiba, which is the combined fully distributed payoff and strategic reinforcement learning. So the general form is like this. So there is, for P1 and P2, so for the first player, there is an update scheme that is on this strategy vector, or this mixed strategy vector. And also there is an update on the estimation of the average payoff. So the same is for P2. So the learning rates are assumed to be satisfying this common condition. So just keep in mind, this is a stochastic algorithm, because every time you generate action, it actually generates stochastically according to the previous strategies that has been played or learned. Okay. So let me just give an example. One of the classical example is this one. So we call it a CRL0. This has been studied in literature for quite a while. So if you look at this, so the FT plus 1 is updated in this way. So it uses the previous FT, and it uses the lambda 1T is the learning rate, and U1T is the payoff you observed at particular time T, and 1, this is the indicator function, basically saying that if you are playing that A1, then this is going to be a vector of everywhere 0, but the component that corresponds to A1 will be a 1 minus FT. So and the estimation of the payoff is you basically use the information from the previous average and plus the information that is you observe from the payoff, the instantaneous payoff that you have received. It seems to be like an averaging of the payoff that you have received. And by the way, all these quantities are vectors. Okay, so if we observe a little bit further, we can see that, well, this F and U are totally decoupled. In a sense, well, in a sense that, well, I should take it back. So F is not coupled with U hat, basically saying that, well, F is not really using the information of U hat. In other words, is that when you do this update, you're not really using any information that you're learning. So basically, it's a very passive way of learning. So you do not, well, you are learning what is the payoff functions, but actually you're not using it every time you're making decisions. So U hat is the estimated average utility function, and you can see it is like a Q function if you incorporate the dynamics. But here, for people who know about Markov decision processes, well, it is actually bears the same form as the Q function, but if you think about there is a transition dynamics. But here we don't have transition dynamics because we're looking at a stochastic distribution over the states. Okay, so this is one learning scheme. So I would love to see this learning scheme as sort of evolution in a sense that, well, you do not really deploy, you do not really make use of the thing that you learn. What you do is just go, well, you just take a look at what you learn and make decisions along the way. Well, you don't even make decisions along the way, just make updates along the way. But there's another learning scheme which we call it RL2. Well, oh, sorry. So this is the same learning scheme, but here, because of decoupling, I'm trying to remove the U hat because people are not really using it. So you can see that if I look at the using the stochastic approximation, it leads to the replicator dynamics. That basically indicates that, well, the previous dynamics is actually a evolutionary dynamics. While thinking about evolution, species are not really making smart decisions, but they are converging to some equilibrium. In evolutionary sense, it's optimal. Okay, so the next scheme is on the other extreme, we call it CRL2. So in this scheme, you can see that while they're also estimating what it is the payoff function you had, but at the same time, they are exploiting that information ft+1 every time using this beta tilde function. What is the beta tilde function? Is the Boltzmann-Gibbs strategy, which is sort of like a softmax strategy, and they basically try to select the largest component of this vector. So you can see this is a very smart learning scheme in a sense that while you really learn what is average payoff, and every time you're actually using that piece of information to make a decision for the next time instant. So this is a very smart decision making. And also, I just want to, this is actually something I want to call your attention, is that this is a softmax function where you can see the denominator is the partition function that it has been studied in statistical mechanics, and it's not really when epsilon is going to 0, it is going to it's an approximation. It's going to converge to the maximum of the maximum function, which is choosing the largest component of the U hat. So you can see this epsilon as this function is sort of mimicking the temperament when you're making a decision, and the stress when you're under when you're making a decision, and not also the knowledge you have when you're making a decision, which is sort of like the when you think about physics, it's sort of like temperature and pressure and the volume. I think that's an analogy when you compare that with the statistical mechanics. So the thing, well, if you think about that type of learning, you can see it is a very smart way of learning. So it's like the human way of learning things. So you really make your decisions every time irrationally, and you really exploit everything that you have explored. Okay, so this is the learning. This is a very active learning. The previous one is a very passive learning because you do not make use of that information when you are learning things. Okay, so I'm not going to that. So again, you can use the stochastic approximation to study the convergence of that the smart learning or active learning update scheme, and this is basically the dynamics you try to study. Okay, so here is one thing that I want to call your attention is that, well, if you try to compare this scheme with which is active learning, and on the other extreme it is the very active learning. So there is a puzzle which is raised by Papadimitrov when he was at EPFL, and he was saying that, well, in one of his presentations and his talks, he was saying that, well, he was looking at two algorithms which were looking for the optimality. One is the simulated annealing, the other one is genetic algorithm. Basically, his question is that, well, the simulated annealing is very good in terms of finding your optimum, but why nature is actually using the genetic algorithm? So I think the answer to that problem might really lies into the discussion that we have here. If you think about the passive learning, even though it is not really making decisions every time using the information that you have already collected, but it actually is robust, okay? Even though it's not very efficient. And if you think about the learning scheme that has been used by a lot of people, and they are very active, but it's very efficient because you're making use of the information every time you learn, but it's very, very fragile because whenever there's disturbance, you're really going to learn something really far away from the truth. So So I think this is really something that why nature prefers the genetic algorithm in some sense, because really robustness is what is really important in terms of making decisions rather than efficiency, because you can still learn to a point eventually after like 1,000 years, but what is important is the robustness. You don't want to change your species from a cat to a dog in one day, right? Okay. So this is a small theorem because I don't want to include so many theorems here. So, but this is something that I want to probably is good to know, is that if you think about the case where one person is learning using the active learning, the other person which is using the passive learning, which is, well, basically one person is one person is very smart, but the other person is very dumb, and they are learning together in the same setting. Well, which could be exactly describing the security setting that I'm talking about. Just because one person the attacker can be very smart, but you are actually in a very passive position, or you're not actually very active, or you don't have that much resources to be active. So in that heterogeneous dynamics, or mixing these two dynamics, one is active, one is not active, you actually can show that these two dynamics together, they are going to lead to an almost surely to an absolute saddle point equilibrium of the expected game, which is the solution concept I pointed out earlier. All right. Okay. So now the talk is about hybrid learning. So what is hybrid learning? So heterogeneous learning is when one person is being active and other person is being passive. When you think about when you're making decisions in your life, you're not making decisions actively every day. Actually, sometimes you're making decisions actively every day. Sometimes you're actually going to be a little bit sluggish, and you don't want to make decisions very active every day. So it's sort of like a linear combination of the two dynamics. You're sort of like somewhere in the middle. Sometimes you are very active. Sometimes you're actually very passive. So if you think about this, so the learning scheme is actually picking from all the possible set of learning schemes that you know, and every time you just pick one of them, okay? So, and also sometimes you might, when you're playing a game, you try to be active, but the other person is not really playing a game. So there is also a set B, which denotes the set of active players at time t. So basically it means that, well, if you really want to play the game with other people, but the other person is not really active or not really in the mode of playing, well, you're not really playing a game. You're not really learning the game at all, right? So that's why we have this BT, which indicates, well, what are the things that you're actually learning when you are making that update? Possibly when you're making that update, you're not really learning anything about the game. You're just learning something that is not a game, okay? So you can do this stochastic approximation again. You can see it's actually, if you in the ODE form, it's basically a linear combination of the different dynamics, okay? So one of dynamics can be the active dynamics. The other dynamics can be a very passive dynamics. And also an interesting thing is that these weights can be evolved at a very different time scales. For example, now you're learning things at 50% of us being smart, and other 50% of the time you are being not smart, but this WILT can evolve a longer time scale. For example, you're probably getting smarter and smarter every day because you are learning a lot of things every day. All right, so this WIT might evolve in an evolutionary sense on a different time scale. So the other thing I want to talk about is the learning in a large population. So the question is, what happens when there are not just two people learning, but actually there are a large population involved in the learning process? So let's say P denotes a population. So one population has this learning scheme, so which is given by this ODE, and what we are trying to look at is what is the fraction of people that use that particular strategy at a particular time. So this is the MP, which we are looking at. So we are looking at there are a set of strategies. I want to see how many people in my population is actually acting in this way, in a particular way. So this is the distribution. to remind you that X is a distribution over A, which is on the action set. So this M is a distribution over the distribution, all right? So in order to characterize this M, so while I have to go through a lot of mean field analysis, but what is interesting with the message I want you to carry away with is that the mean field analysis, the mean field dynamics, this M, the solution of this M is basically given by a partial differential equation. So this partial differential equation is analogous to the Fokker-Plane equation if you include the stochasticity here. Without stochasticity here, it's just 0. So this coupled partial differential equation, this coupled partial differential equation, because every population has a partial differential equation, characterize the large population learning. Well, sort of like in the same spirit of ensemble control, if you think about it, but in a very large population sense. Okay, why it is interesting for us to study, because a lot of times we're dealing with the large-scale games. We're not dealing with a game of like only 2 persons, but a game with a large population. Okay, so here an example, but but I'm not sure I have time to do that. Only 1 minute, right? Yeah. Okay, so here an example where basically we're playing a game. The attacker is playing a game with the administrator. So I'm just going to show you some results here. So here is when everybody is using the active learning scheme. You can see there is a lot of oscillation here because, well, obviously, because this is not robust, but whenever you're learning something wrong, it's likely that you're going to deviate from the real equilibrium. And this is one everybody is. This one is the payoff vector, and this one is the strategy vector. And when everybody is trying to learn using the smart way, you can see there will be a lot of oscillations just due to the it's not very robust to disturbances. But if you look at the heterogeneous learning, when one person is acting when one person is acting smart, but the other person is acting passive, you can see it goes to an equilibrium a lot faster. All right. Okay. So this is the payoff. This is the payoff vector, and this is the strategy. You can see while it does go more, the curve is more smooth because one person has the property of robustness, and the other person has the property of efficiency. So that's why it converges a lot better. All right. So the take-home message here is we're looking at a hybrid learning scheme. So there's a lot of questions that is open that possibly needs to be studied. For example, a lot of convergence issues. And what is the message here? The learning scheme that we look at is that people do not need to know their payoff functions. People do not need to know their action spaces. And people do not interact at all times. And players evolve at different time scale, which is actually a different element if you from the conventional classical algorithm people study economics about game theory. And also, the hybrid learning reflects differences in preferences and rationality, which also quite an issue that people brought about in game theory, because that's always the issue about rationality. How do you model rationality? How to model the preferences? And also, the hybrid learning yields a more practical model for the application that we are targeted. There are so many other work to do, so if any questions, I'd be happy to answer at this moment. All right? Hope I didn't lost you.